commonly about 3 general formats as far as getting solar electricity connected to the grid. The most popular for a long time is what we called a string topology. In this case, you connected a group of solar panels in series to increase the DC voltage, which is then brought down somewhere between typically 200 to 600 volts DC to the inverter. The inverter then converted that high voltage DC into utility AC, which was then connected to the utility lines on your side of the meter. Well, the issues associated with that were very simple. Obviously, you had to be very proficient at understanding direct current, which is something that not all electricians weren't commonly acquainted with. They weren't trained on DC. Second, solar panels vary slightly. One is a little bit weaker than another, then the entire string performs to that level. PVAC modules take the inverter and attach it directly to the solar module, in this case the photovoltaic module. It is not one that you buy separately from the PV, if you will. It comes as a complete unit. The solar module and the inverter are one product together. As you can see here in the photo, we've got a group of the AC modules here in a part of a larger array. Then there's hybrid systems, which is the direction a lot of folks are going, because if the utility grid goes away and you do have solar on your home, a lot of people are saying, well, I'd like to be able to use that as a backup source of power for my home. I'd like to at least maybe keep my telephone, or some people say refrigerator, or other what they consider critical loads going. So the hybrid system actually allows the solar electric to separate your home from the utility grid in the event of a power outage, and then continue generating power until the utility comes back, at which point you get to reconnect. Now, here's a pictorial showing basically the complexity of a string system, where you have a series of photovoltaic modules on your roof or elsewhere, all connected in series. Issues here are, again, if you have a weak panel in the series, or heaven forbid you should have one that does fail, then the entire string goes dead. It comes down through a DC switch where you disconnect those photovoltaic modules from the rest of the system. That is a UL and National Electric Code requirement in this case. Then you have a ground fault circuit interrupter, sometimes called a GFDI, which is ground fault detection and interruption, in case you end up with a very slight, what's called leakage current, occurring somewhere in the system where it should not. Then you've got the inverter, and then an AC switch that allows you to disconnect everything from the utility, and then finally the utility panel itself with the circuit breakers and so forth. Problem here is that it takes a lot of wiring here. The DC wiring has to be kept separate from the AC wiring. Again, that's the National Electric Code requirement. The wiring itself is high voltage. It's lethal if it's not handled properly, and there have been fatalities associated with situations such as that. You end up having to match the PV. This is not quite the issue that it was a number of years ago, but if you have, let's say, a plus or minus 3% tolerance on the photovoltaic modules, and all of them are running very, very well, but you have one in that group that's, let's say, minus 2.5%, then the entire string is down by whatever that weakest panel is. You have to optimize, in effect, the entire system for the best performance, if you can do it. Generally, it takes more time, it adds expense to it and everything else, and most people just simply don't take the time. Then the inverter itself dictates the size of the system. If you wanted to, say, double, you have to turn around and literally duplicate everything that you've got here. If you wanted to add to it, it becomes a very expensive proposition and a very large step upward to go from here to the next increment and so forth. Space usage is also constrained by shading. Let's say you've got room for 17 panels on your roof, and whether it's another building or a neighbor's tree or something else that would prevent you from getting good sun, maybe you need 18 panels in the entire system, and you've only got room unshaded for 17. It makes it a little bit awkward. The AC modules in this situation, you could actually install all 17 and the system will run just fine. We don't have a shading issue like you do in the larger string systems. So now we're looking at a thing, what if the PV produced AC very directly? This is an example of an AC module-based system where the inverter is present on the back of each one of the photovoltaic modules. Each one of those is actually producing grid-ready AC. In our case, the inverter is already attached to the photovoltaic module. It is not something that you buy separately and then have to go to the trouble of mounting it, grounding it, and connecting it. All that's been done for you. There's only one connection involved here with our AC module inverters, and that's just a simple clamp connection onto the AC cable wherever you want it to go. So in this case, you can start with as few as one and grow the system as large as you've got roof space. Another interesting item here is that, let's say, some of the older string systems, as solar panels have evolved, their wattages have changed, their physical dimensions have changed, and if you do have a photovoltaic module that gets damaged, let's say by hail or other cause, 5 years down the road, we're finding it sometimes a little difficult because they're no longer available. You have to replace a string module with one of identical characteristics, or the entire system is affected in some manner. Either you'll be buying one that doesn't fit because it's mechanically larger, or its wattage and voltage and amperage characteristics don't match. It becomes quite a chore to find something 5, 6 years down the road. With AC power coming out, you're already connecting into the circuit itself with AC, and it doesn't matter if you've got, let's say, a panel that's 180 watts and then another one that's 240 and then another one that's 260. As long as you observe the amperage characteristics of that circuit, you can connect just about any size AC module system together without any of the headaches that you have in the string system. Now, people look at it and they're seeing an awful lot of inverters, what they're calling micro-inverters, coming onto the market today. Exeltech has been around for 21 years. We've been actually doing parallel systems for the better part of almost 21 years. You take a look at our AC module system, you don't have to go through the headaches of matching the PV. You don't have to go through the DC disconnects. You don't have fusing for the DC side. You don't have the ground fault detection and interruption. You don't have any of that hardware, separate conduits or anything. So that results in a lot less time to install, a lot less time to, you don't have the extra hardware involved, so it's a lot lower cost. You have half the wiring approximately, because with the DC side gone, you don't have the DC side to calculate or to estimate or anything else. You have fewer solar-specific skills. With the elimination of the DC side, we've suddenly opened it back up to a trained, skilled electrician. You don't need to even have the PV facing in the same direction because they're all independent. So if you're sitting, let's say, with your home in a cul-de-sac and part of your roof faces a little bit to the southeast and part of it to the southwest, you can go ahead and install a system that way, and each panel will perform to its maximum capability without affecting any other. So every module, every photovoltaic module is optimized with its own individual inverter. You don't have the issues of what we call mismatch losses as a result. You end up with shade. If you do have shade, and shade happens, I mean, in everybody's system, you may get a leaf that blows across and lands on a panel somewhere. It affects just that one panel. It does not affect the entire system. You also have in this situation an optimal communications module called the heliocentric, and that allows you to individually monitor and track the production and performance of every one of the PV and inverters in that system. So where you look at it, all of this enhances the reliability. You have no true single point of failure. Our AC output from the inverters does not pass through each other. You don't have the output of one inverter connected to the second inverter and then the third inverter in line. They all share a common, what we call, home run cable. And that's done through a single connector that just clamps to that home run cable. So the AC power does not pass through inverters. It is completely, in that sense, reliable. You do not have any single point of failure to affect you. The AC modules themselves are completely environmentally sealed. It is what we call convectively cooled. There's no fans, there's no moving parts or anything else, and they do come with a 20-year warranty. So, with no DC side wiring, none of the issues associated with a conventional string system, they're not only faster and lower cost to install, but they're safer. Now, in terms of the customer side, you have more uptime even if one of the inverters were to fail. And they are electronic. Something may happen. You can't guarantee transistors are going to live forever. But if one inverter fails, the remainder of the system continues to function without being affected. You don't have to go through and match the PV. For installers, that is a big plus. The individual PV breakage we talked about. If you have a problem, in Texas, we don't get hail, we get bowling balls. It happens. Panels get broken, but it affects only the broken panel. The rest of the system continues to function. You don't have to match them. You can add to them at any time. This is a huge plus. You can start out with one, and if your budget only allows one at a time, then add them one at a time. You don't have to buy 10 or 15 or 20. You don't have a set number to establish a system. A string system topology requires that you have a specific number to match the inverter. Those are a temperature-governed aspect because the photovoltaic characteristics change. They actually work better when they're really cold, and a system that might work well, let's say in Minneapolis, especially during the winter, may not work properly at all in Phoenix in July. So you actually literally have to design the system for your particular geography and your location and the weather. What happens if you don't have quite enough space? Maybe you need room for maybe 10 panels for a string system, but you've only got area for 8. That's fine with the AC module approach. You can put up those 8 and utilize your available space, whereas you may not have enough room for an actual string system. Now, this is a commercial installation. It's with a number of string inverters. These were all connected with the PV outside, and this was the wall. You can see the individual disconnects for each inverter. We take all of that and we move it to the back of each one of the photovoltaic modules. So if you had started out with our system, the photo that you're looking at right here would have become this. All of that hardware goes away. As you can see, there's a couple of conduits coming in now from the top. That's the AC run coming down from the roof. That's all it takes. You can see how much cleaner it is. You don't have to worry about it being environmentally sealed. You don't have to worry about people accessing it. You don't have to worry about all the extra headaches that are associated with a string system. Again, shade happens. We talk about it. In some situations, you have homes that are not completely facing south. Not a problem. You put what you can facing south, you put what you can maybe facing southwest, as in this example, and maybe there's a taller building that happens to shade a panel or two later in the day. The other 4 panels that you see in this illustration continue to operate at full power because they're not shaded. In an ordinary string system, this could have knocked it completely offline. Another comment, this is actually building integrated photovoltaics. The dark stripe around the middle are PV modules, and they're not all facing in the same direction. In fact, the curvature of the building would not allow them to. And here, each one of those PVAC modules with our inverter attached is going to produce its full output power irrespective of where the sun direction is and irrespective of the fact that they're not all facing in the same direction. Now, kind of a simplified block diagram, you can start out with as few as 1. If that's all your budget or space permit, start out with that, and let's say 6 months down the road, maybe I want to add to it. Add several more. Somebody asked, well, gee, is it, you know, I've got 240 volts. Will they work into a 240-volt system? The answer is yes. Our inverters are 120-volt AC output. You can connect some from line 1 to neutral in a home or business, and others from line 2 to neutral, and you'll still maintain the balance the power company wants you to see. And yet, with some working line 1 and some working line 2, you can still effectively have a 240-volt system using 120-volt modules. Just as in your home, many of your loads are 120 volts. You also have 240. The power company just simply wants to see approximately a balance when you're backfeeding power. That's one of their great concerns. Not a problem here. Now, again, common thing, everybody says, hey, I would love to have this thing operate. I want to be able to at least have some electricity if the power goes off. Can I do it? Yes, if you configure the system properly, an optional inverter can be set up in the home with batteries that allows it to look to the AC modules like the grid. And in that situation, you don't have any kind of worries as far as being able to provide the power. You've got your photovoltaic system running on the roof. If it's, let's say, a storm or something comes through and the lights go off in your neighborhood, the PV system will disconnect you from the grid and allow you to form what we call an intentional island. So you've got batteries involved in the system. It's a little bit more complex, but a system can start out, again, with just one and grow. Or you can start out with it at this level. It's just a matter of time and budget. This is a full-blown system. And see where it says multi-phase capability, this is key. A lot of people look at it and think 120 volts output is a negative, but if you're a little bit savvy about electricity, you'll understand that it will work 120 volts, they'll work in pairs in 240 volts, and if you have what is called a 208 volt three-phase W-Y-E, that's a 4-wire three-phase system, we can also connect and work in 208 volt three-phase as well. That's what you're actually, you could grow the system here from 120 to 240 to 208, and that means our AC modules will work into small and medium-sized industrial and commercial environments. Now, this is one of the keys. We have an optional whole house energy monitor that works in conjunction with our AC modules. The interesting thing about the whole house energy monitor, we call it the Heliosentry. It includes clamp-on current sensors. These are a special, like a donut-shaped device. You do not need to touch your internal house wiring, but would recommend an electrician do this. And you can actually monitor the power consumption for your home on both line 1 and line 2, as well as the total power consumption, but you can also monitor the total backfed power. The Heliosentry also comes in with several other sensors. It comes in with an irradiance sensor. It's calibrated in watts per square meter. That irradiance sensor allows you to see how much sunlight you've got. If you don't have an irradiance sensor, and let's say that you've got some AC modules on your roof and they're only running at 80%, is that because there's only 80% sunlight, or is there another problem? With this, you'd be able to tell. It also tracks temperature. The irradiance sensor for the photovoltaics includes a temperature sensor, and so you can track the temperature of the photovoltaic modules. You can also track ambient temperature. You can also track the internal temperature of your home, if you wish. The unit itself is Wi-Fi enabled. It comes in with 802.11g. It will automatically can be configured to connect into your home network. If you so choose, you can put this information on the net. Some of the people do. Some of the people wish to keep it private. Best of all, there is no monitoring fee associated with the Heliosentry. This is yours. We provide it with free software. The communications from the individual AC modules are by power line communications down to the Heliosentry. Bottom line is, everything that you need to monitor in your home can be done in terms of total power consumed, total power backfed, can be done through the Heliosentry. The neat thing about it is that if you can measure it, you can monitor it, you can track it, and you can reduce it. Probably the greatest thing in terms of keeping track of people's gas mileage has been that little miles per gallon meter on the inside of some of these new hybrids. No one single instrument has ever provided better improvement for gas mileage than that. Here you get real-time monitoring of your home's power consumption. And if you really wanted to get, ambitious with the data, it can be exported out in comma delimited text format and drawn into a spreadsheet, and then, boy, can you manipulate it from there. Now, this is optional, but we obviously recommend it. The power line communications from the AC modules communicate directly with the heliosensory, and from there, you have got an entirely user-configurable screen. I realize the one that you're looking at right now looks fairly busy. You can close any or all of those boxes. You can open whatever you wish. You can enlarge them to whatever you wish. The scaling is something that you can do manually. You almost want to look at, let's say that you can see in the upper left corner, each one of the individual modules is being tracked in the top left. The two gauges on the right are showing the ultimate total energy production or consumed. But now you can see in the next set of boxes down on the left, the solar irradiance and the output from the system. The next box over shows, in this case, we've got a refrigerator that's cycling on and off through the course of the day. That's the reason it looks a little bit fuzzy, but you can clearly see the contribution of the total power consumed by our home, and in this case, the reduction provided to us by the AC modules. These are all individually scalable. You can even change the colors if you wish. These just happen to match the screen very well. So at that point, we've got a complete system. This can be installed with or added to your system at any time. It is not required, nor do we require it as far as maintenance for the system or anything else. There's some other things that we can discuss later on that.
And this is Rick again, and just to make clear, it's not required, but it's free if you want it.
Well, the software comes free with the unit. The monitor itself is an add-on that you can have installed with the system, which is something we do recommend, but not required.
Okay. Well, thank you very much, Dan. We're now at the questions and discussion portion. So if you have any questions, please type those into the chat window. I have several that have come in already. One of our attendees, Ken, with principal at Solar, has sent me some. Before I start on his list, I wanted to take the liberty as a host to ask a question. Dan, you've talked about a lot of small systems and how the PVAC modules have advantages there, several panels, kilowatt size. I'm wondering, where do you think the boundary is between when a panel-specific inverter makes sense to convert to a central inverter? Is that in the hundreds of kilowatts, in the megawatt scale, or what exactly do you look at as that as the sweet spot for these units?
Well, generally speaking, we find that 100 to 250 kilowatts tends to be kind of a gray area as far as the overlap. The central inverters, just simply due to economies of scale, can be manufactured at a lower cost per watt. But if you start looking at overall power production, let's say that you've got a central inverter system and you have what's called a power purchase agreement, you obviously want to produce as much energy as you possibly can. And studies have shown that individual inverters mounted on the backs of the photovoltaic modules can equal or exceed the energy output from a central inverter, and in some cases by several percentage points. And over time, that adds up.
And so you think that this type of unit would always win under 150 kilowatt size or so, or is there a gray area that needs to be considered? Where's the size where this type of unit should always win?
Well, clearly anything probably below, up to 100 kilowatts would be almost a definitive win for a system.
200 would be a
somewhere in that area, and there are going to be instances where a central inverter may be the preferred choice.
Excellent. Well, I'll start going through these questions and put Dan on the hot seat here. The first one we had from Ken at Principal Solar was, what effect does direct exposure to the sun and roof heat have on the reliability of the panel inverter to perform?
Well, normally electronics degrade with heat, and that's a given. Over time, it's almost like running your tires at 100 miles an hour. They're going to wear out faster than if you're driving, let's say, at 50. One of the big concerns, particularly amongst people who have a little bit of electronics knowledge, is what a component called a capacitor, electrolytic capacitor. And you and I were discussing this a little bit earlier before we went on. Tires, say 30 years ago, I remember buying tires with a 20,000-mile warranty, wear-out warranty on them. Today I'm buying tires with 80,000-mile wear-out, and I've gotten much better than that before I've had to replace them. The component, this capacitor, over time will wear out, but the newest technologies we have found will last, and we have done extensive studies on this, somewhere around 80 to 83 years in our equipment in Phoenix, Arizona. And that is the worst case environment as far as heat. If you take it somewhere where it's a little bit cooler, those capacitors, the longevity is going to be even greater. If you take a good quality part to start with and you do it, you incorporate it with an intelligent design, the capacitors are not a concern. That's kind of a marketing hype by people that have decided, I'm going to go out and not put them in, and then I'm going to try to sell people on the fact that somebody else has these. Well, the advantages to the electrolytics is they are smaller and they are lower cost than alternate components that will do the same job. But again, you know, after, and we test these units, for example. Somebody said, well, how hot are your units designed to handle? We specify them for normal operation up to 70 degrees C, which is about 156 Fahrenheit. We actually test them to 90 C.
That's almost as hot as my attic here in Dallas in the summer. Well, okay, great. I had another question that came in about noises. What's the noise level increase in decibels caused by having several inverters on each panel versus a single DC string system?
Well, the DC string system is only going to be noisy if you've got a fan or other mechanical device moving it. Sometimes they do hum or buzz hanging there on the wall. The AC modules being mounted on the PV, first of all, are going to be outdoors and completely away from everything. And number two, they're silent anyway. You can't hear them. There's nothing to vibrate. There's no moving parts. It's all convectively cooled.
Oh, excellent. And here comes another question related to warranties.
Warranty.
Yeah, what warranty comes with the Exeltech system to offset the increased potential for inverter failure as a result of having several inverters used instead of just one inverter in a central DC string system?
Well, our AC modules come with a 20-year warranty. And the nice thing about these is that it just takes, if you should have a failure under warranty, and it's a warrantable failure that we can replace the unit, it just takes 4 screws to replace the individual AC module. There's only 4 screws holding it to the back of the inverter, I'm sorry, to the back of the PV in this case. You remove those 4 screws, you don't have to touch wiring, you don't have to do anything. It'll take you longer to get up to the roof and lift the panel. It'll take you about 1 minute to exchange the inverter should it ever fail. It's just those 4 screws and no wiring to mess with. So 20-year warranty right now.
Yeah, and that was actually one of the follow-up questions was about the replacement of an inverter. Does it take an electrician familiar with the panels if an inverter were to fail to replace just one inverter on a panel?
No, it doesn't take an electrician, but if you're not, let's say you're not experienced climbing on your roof or getting up to heights and so forth, that is still something that you should leave to a professional, whether it's your solar pro or somebody of that nature.
Would a roofer be able to?
A roofer could probably do this. In fact, they're the ones that are even most qualified to install the racking at this point.
Really? Well, that's excellent. Well, usually we don't talk about different company-specific products, but several questions have come in about the N-phase system, which many people are familiar with for the micro-inverters. They kind of help to coin the phase in the industry. So I guess the summary would be, what is the Exeltech advantage over an N-phase micro-inverter?
Well, we often get compared to N-phase. N-phase starts out as a standalone micro-inverter that you buy separately from the PV. You have to first of all be certain that the PV that you're buying is a match for that particular inverter. Then during the installation, you put in the racking. Then you mount the inverter to the racking or some other mechanical surface. You then have to ground the N-phase, which our inverters are certified to UL 1741 grounded through the utility. We do not require separate grounding. Then you have to attach the PV to the racking, connect the DC wiring, then you connect the AC wiring, and so forth. In the event that you should have one of theirs fail, you will find that you have to reverse that whole process in order to replace it, whereas on ours, as I mentioned, it was just those 4 screws. Also, one more thing, because our wiring is completely concealed on the DC side, the National Electric Code and UL do not require that we have a ground fault detector or interrupter inside our equipment. There is no place for that leakage to take place, so it allows us to eliminate components, it allows us to reduce the cost, and parts that get to be left out aren't there to fail.
Okay, and there's, again, a follow-up question to that was, how do the losses in the Exeltech system compare to the losses in a DC string system at the grid connection point?
Well, in this particular case, common design practice dictates that you put a system together in a string configuration with approximately 2 to 2.5% loss, somewhere in that range. That's the best compromise between loss and the copper cost in the wiring today. All of that goes away. We don't have any DC side wiring. So in our particular application, that is a win for us. We also eliminate any of the bypass diodes that are also a loss element. We eliminate the DC connections. We don't have any expensive cables. You don't have the MC or solar lock connectors. All of those are gone. And those are a cost savings ultimately to you. Long term, we gain about 2 to 3% that would have been lost on the DC side by being attached directly to the PV.
Oh, excellent. So it does a little better. We're out of time, but I just did have one other question, and it's related to, I can vouch for this firsthand. We are actually broadcasting today from Exeltech's manufacturing operation in Fort Worth, and the question that came in was, are all components made in the USA? Dan?
Well, when you say all components, the individual integrated circuits come in from all over the world, the various sub-little parts, but ultimately, we design everything right down to the circuit board right here. We assemble them here on our factory in Fort Worth. We wind our own transformers. We do all of that kind of work that we can do here. The demand has been such that we're not able to keep up with it at the present time. So while we do manufacture as fast as we can right here in our Fort Worth facility, we've also gone out and hired an outsourced contractor with our design, and they're building it to our specifications to help us keep up. But to answer your question, yes, everything that we do here, we have got right here in Fort Worth from the circuit boards on up, and then we outsourced some of the extra, if you will, the overflow that we just simply couldn't handle, but the good news is we're looking at putting on additional shifts to handle it.
Great. All right, well, we are out of time, so thank you all for attending, and thank you very much to Dan for your time here to present. You see his contact information. You can contact him via email or myself, and this webinar has been recorded, and it will be available within about 24 hours on our website for those of you who might have missed. And have a great day. Thank you.